The binomial distribution, what it's looking at is what happens when you have an experiment which has only two outcomes. And we usually talk about those two outcomes as a success and a failure. So if you're flipping a coin and you want heads, heads would be the success, tails would be the failure. If you're rolling a die and you want a 3, the 3 is the success, everything else is a failure. And so you can have experiments that look at, well, what are my chances of flipping a coin 10 times and getting 3 heads? How do I figure out the probability of that? Okay, so we have probability of success, we use letter P, probability of failure, we use letter Q, and it's always 100%. There's no other options. You either get a success or a failure. It's not like a maybe success or a maybe failure exists in there. It's one or the other. So these are the properties. You do a certain number of trials, like you flip a coin 10 times. On each trial, there's only 2 possibilities, heads or tails. Each trial is independent and identical. It's not like, ooh, this coin has started to be flipped 10 times, it's now changing shape, and it's more chance of getting heads now than before. No, that doesn't exist. Each trial is exactly the same as before. Probability of success is the same. Probability of failure is the same. Now, the reason we did our combinations review, our binomial theorem review last class, is because the probability distribution function looks like this. Very similar to your formula for the binomial expansion. So right now, this formula looks complicated. Yes, it's connected to your binomial theorem. We will do some examples and start to break it down and figure out why does this work and what does this mean. So first of all, this is Px equals R. That was the bottom part of your probability distribution chart. So we've got some sort of probability function. It's binomial. There are 6 trials, and your probability of success is 0.4. So in the yellow highlighted part, that would be the way that we would write it. Okay? If we wanted to figure out each individual chance of success, there's our formula. For example, if you wanted to find out exactly when x is equal to 4 in another example, you would plug in 4 for r. Now, these are just plugging things into the formula. Again, at this point, I don't really feel like we know what's going on. We're just got a formula, plugging it in. So we're going to do a simple experiment where we're going to roll the dice 3 times. And we want to see how many, our probability of success is getting a 3. So if you roll a dice 3 times, you could get 0 3s in total. You could get 1 3, 2 3s, or 3 3s. So as far as our probability distribution chart looks like, right, you could get 0 3s, 1 3, 2 3s, or 3 3s. Okay? Your number of trials is 3 times. This is a binomial experiment where our number of trials is 3 times. Our probability of success is 1/6. So according to the formula, if I want to find this first one, the probability that x equals 0, according to the formula, I would go 3 trials happening 0 times. Probability of success is 1/6. That's happening 0 times. And the probability of failure, 5/6, happens 3 times. Yes? Well, if I was rolling, because I'm saying I'm taking a die and my success is getting a 3, right? So there's only 1 out of 6 chance of getting that 3 when I roll the dice. I mean, you could make a tree diagram for this, right? 3, not 3. Second time you could get a 3 or a not 3, 3 or a not 3. And the third time, same thing. Does it make sense that this 0 is only represented by the branch that's not 3, not 3, not 3? And each of those branches will be 5 out of 6, 5 out of 6, 5 out of 6. Look at our formula. Our formula says 3 choose 0, that's 1. 1/6 to the 0, because it never happens, that's 1. And then we have our 5/6, 5/6, 5/6 to give us 125 over 216. Okay? That's branch 1. Now, we can take out our eraser and say, wow, that's a big eraser. We can take out our eraser and say, let's go to x equals 1. So how does that change things? Now in my formula, these would be 1s, 1s, and this will be a 2. Where do these numbers come from? Well, 3 choose 1 is 3. And I'll have 1/6 multiplied by 25 over 36. Multiplying that all out will give me 75 over 216. Look at our tree diagram. In order to get 1, 3, does it make sense that you would have to have not 3 twice and 3 once? How many different ways does that happen? You could get your 3 once here and then not 3, not 3. You could get your 3 once here, not 3, 3, not 3. Or you could get your 3 here, not 3, not 3, 3. The 3 choose 1 at the beginning is choosing where your 3 is. And it's telling you that there are 3 separate cases where that could happen. Then you will always have in those branches a 1/6 and 2 5/6. Does that make sense? And so that's where your 75 out of 216 occurs. If we put in the second time. So now I want to find the probability when x equals 2, that would be probability of getting 2 3s. Well, 3 choose 2 is still 3. The 1/6 would happen twice. The 5/6 would happen once. Multiplying this out gives us 15 out of 216. And finally, the last case is getting all 3 3s, the least likely option. We would now have probability x equals 3. 3 choose 3. The 1/6 happens 3 times. The 5/6 doesn't happen at all. The 3 choose 3 is telling us there's only one branch where that's going to happen in your tree diagram. The 1/6 in that branch happens 3 times, which gives us 1 out of 216. And if we add all of these up, 125 out of 216, 75 out of 216, 15 out of 216, and 1 out of 216, that adds up to 100%. So if I decide to roll this die 3 times, it's very unlikely that I'll get all 3 threes. It's most likely that I won't get any 3s at all. Okay? But I could get 1 3, and I could get 2 3s. So that tree diagram and the probability distribution chart helps explain what the probability distribution formula is. What we did in examples, in the next examples, was find out specific ones. In a binomial distribution where you did 5 trials, obviously you don't want to draw the tree diagram anymore because it gets really big. It'll have 32 branches in the end. The probability of success is 60%, so a lot of the branches will have 60%, all the not branches would have 40%. What are your chances that you get exactly 4 successes? Well, the 5 choose 4 would tell you there would be 5 branches that have that. And each of those branches would be the same with 4 successes at 0.6 and 1 failure. It's just a matter of where the successes and the failures would be in those branches, and that's where a combination comes into effect. Okay, so that's a lot of information to kind of have in your head of what's going on in these situations. And then the formula breaks it down to allow us to figure out something quick and easy. So now we're going to see if we can get this into our calculator. So we turn on our calculators. And we go second distributions, which is the VARS button. And the binomial distributions are hidden on the second screen. And with the newer calculator, it says, how many trials do you want to have? So on ours, we had 5 trials. The probability of success was 0.6. We want to find getting exactly 4 successes. And we can paste it and get the answer that quickly. So what this means, since these are almost always calculator questions, is that you can get answers very fast without even having to use the formula. But you have to know how to get to this part of your calculator and how to get that answer. Okay? If I did it again, second distribution, binomial PDF, if I did it again and didn't put an x value and pasted it, it gives me them all. So I could fill in my probability distribution chart. So if I look at this answer here, I've done 5 trials. My probability of success is 0.6. This 1% would be my chances of getting 0 successes. 7% get 1 success. 23% chance that I'll get 2 successes. You can arrow over here and get all of your values. Sometimes what's really nice with something like this, since all the data values are all over the place, is you can hit your store button and send it to a list. So I'm going to store it in list 2. And now when I go stat and edit, all of those data points that I had are stored in list 2. And I can actually, I don't know what those numbers are for in list 1, but they look pretty. Oh well. 0, 1, 2, 3, 4, 5. And I've just created my probability distribution chart in my statistics list. So I can now easily see that if I have 5 trials with a 60% chance of success, it's most likely that I'll get 3 of them to be successes. But there's only a 35% chance of that. Questions? A manufacturer finds that 30% of the items produced from one of the assembly lines are defective. I would close that assembly line if I owned this business. 30% is terrible, okay? But during a floor inspection, the manufacturer selects 6 items from this assembly line. What are the chances that 2 of them are defective? Whew. This is the thing about probability distributions, is we can now answer questions that if you would have read them yesterday, you would have said, wow, that's a lot of math. I think I will pass. Or you might still say that today. You're still saying that right now. Does that not sound complicated? Okay? So one of the things that we have to get good at in this unit is the recognition. The recognition that this is a binomial distribution. We can recognize that because A, there's a certain fixed number of trials. In this case, it's 6 items taken from the assembly line. B, there's a success and a failure. It's either defective or not defective. And with that, we can set up and say, I want to find the probability that x equals 2, the probability of success, and in this case, success is getting a defective one, is 0.3. And so from my formula, I can do 6 choose 2, 0.3 to the 2, 0.7 to the 4. So again, a little reminder from our formula, that would say if you drew a tree diagram for this, you would pick all the branches that have 2.3s, because that's 2 failures, and 4 good ones, non-defective ones. On your, the amount of branches that would have that would be 6 choose 2. There would be 15 branches that have 2 defectives and 4 good ones. Multiplying all that together gives us a 32.4% chance. We could also just use our calculator and go to Binomial PDF and write in there's 6 trials, our probability of success is 0.3, and I want to have exactly 2 successes, and that would add that, give us that result. Yes? How did I get the 0.7? This 4 here and this 0.7? So because there's 6 trials, okay, and we want exactly 2 successes, that means our probability of success is 0.3, and it needs to happen 2 times. Our probability of failure is the other 70%, and that has to happen 4 times. So these 2 numbers will always add up to how many trials you have. In part B, if you want to say what are the chances that there's at least 2 of them that are defective, the long way of going about this is you could figure out the probability x is 2, then figure out the probability x is 3, then x is 4, then x is 5, then x is 6. Do all of those separately and add them up. Or you could do the opposite and say, if I figure out the probability that there's no failures, or the probability, that there's no successes, no defective ones, or only 1 defective one, and subtract that from 1, it will also give me the result. And a second way is introducing the Binomial CDF button on your calculator. So, I'm going to let you finish writing this down. We're going to revisit our example of rolling the dice and getting a 3 and look at the Binomial CDF for that and what it means. And then we'll come back to this question and understand what the binomial CDF means in this question. So we're going to look at our original example, which we have our tree diagram, which we've already figured out our probability distribution chart. This was us rolling the dice and saying, what are the chances of me success being getting a 3, failure not getting a 3? And we're now going to go to our calculator and second distribution and go to the binomial CDF to see what that does. So binomial CDF, we're still doing 3 trials. Our probability of success is still 1/6. We're not going to put in an x value because if we leave that blank, it will calculate them all. And now I'm going to store this, store into list 2. And I don't like those numbers, so I'm going to see. Did it work how I wanted it to? No, because I had 5. Where is all of my, sorry. I have to go back. 3 trials. I'm going to put, I had different numbers in there. That's why it didn't make sense to me. These are the numbers that I want to put in. I should have these as decimals. 3 trials. I'm going to re-put this in to list 2 and put my, here, so I can quit. I want to store this one into list 3. And I am going to do my binomial PDF into list 2. Same experiment, 3 trials, probability of success 1/6, and store that one into list 2. You can delete this and delete this. So we had our chances of getting no 3s was 58%, that 125 out of 216. There's a 58% chance that we would get no 3s. There was a 34% chance that we would get 1 3, a 7% chance that you would get 2 3s, and a very small 0.5% chance that you would get all 3 3s. The CDF adds them up as you go. Kind of like your cumulative frequency chart added up things as you go. The C stands for cumulative, and so there's a 57% chance after 0 because it has only added the 1. But if I take 57% and add 35%, I'm going to get 93%. And then if I add another 7% to that, I'm at 99%. And if I add them all up, it makes sense that you would always get 1. And so what a cumulative frequency does is it adds up the values up until a point. So if we go back to the example that we just finished, and we look at what this means here, the binomial CDF of 6 trials with a 30% chance of success, cumulative up to 1, would add the 0 and the 1 together. And if we subtract the 0 and the 1 from 100%, we would be left with everything else, which would be at least 2 being defective. So we are introduced to our binomial CDF and what it stands for. So here's an example. Binomial CDF 3.52 says if you did 3 trials with 50% chance of success, like flipping a coin, it finds the cumulative probability of finding 0 heads, 1 head, and 2 heads all together if you toss that coin 3 times, which is 0.875. I'm assuming that's the numbers. I'm going to type it in just to make sure. The C stands for cumulative, and it's adding it up, of a distribution frequency. So we had 3 trials, our probability of success is 0.5, and we're calculating up to 2, 0.875. So how could we describe this? Getting 0 heads, 1 head, or 2 heads is the same as getting at least 1 tail. If you flip it 3 times, if you flip a coin 3 times, your chances of getting at least 1 tail are 87.5%. As a fraction, this is 7 out of 8. If you think about what's the opposite of at least 1 tail, no tails, or all heads. If you think about your tree diagram, can you see that there would only be 1 branch that would have all heads, and it would be 1/2 times 1/2 times 1/2, or 1/8, 12.5%. Okay? Sometimes we get our cumulative frequencies asked in this notation. What is the probability that x is bigger than or equal to 2? Anytime you're trying to figure out the probability of x bigger than or equal to 2, okay? And here's just another random example. Sorry, this is not connected to the stuff above. Again, one of the things that can help you imagine this is, say, if you had 6 trials, what would your probability distribution chart look like? It would have how many things in it? If you have 6 trials, my probability distribution chart would have 7 things, because you could get either 0 or all of them. So there's always going to be 7 things. If I want to find the probability x is greater than or equal to 2, that would add up all of those ones. Does that make sense? Now, the cumulative frequency just adds things up as you go along. So on your cumulative frequency, does it make sense that if you wanted to have all of these, you would have to subtract what those 2 are from 1? And that is what this part is doing. It's saying, binom CDF, I'm going to add things up as I go along. And if I add them up to 1, that's those green ones in that box. Subtracting that from 100% will be what I'm left with, which is all of those red ones added up. So really connecting this new idea to your probability distributions is the important thing. The nice thing about binom PDF and binom CDF is it's going to allow us to get examples with much bigger trials that drawing the tree diagram would be exhausting. And calculating everything would take forever. This allows us to calculate it quickly and get answers faster. Right? Sophie has 10 pots labeled 1 to 10. Each pot and its contents are identical in every way. She plants seeds in each pot, and the probability of these seeds germinating based on historical studies of whatever plant she's planting, hopefully it's legal, well, okay, is 80%. Oof. What is the probability that all 10 of them sprout? Right? So this becomes a binomial PDF. I don't know why, maybe it's just me, but over time, I've always found that no matter which question I'm reading, these binomial distributions take me aback at the beginning. Sort of like, whoa, this seems hard. And then I have to go, oh, this is a binomial distribution, and then it becomes easy. But on first reading the question, it seems, oh, this is hard. And I think it's partially hard because your brain doesn't have any kind of way to calculate all of these numbers to figure out this probability. Is it going to be a good chance or not? Well, what do we want to find? There's 10 trials. Probability of success is 0.8. That's how we know it's a binomial distribution. We can use our binomial PDF, probability distribution frequency. We want to have exactly 10 of them. And there's only a 10% chance or an 11% chance that this will actually work. You could also have used your formula, 10 choose 10. Okay? Again, if you think about drawing a tree diagram for this, your tree diagram would have 10 things, one for each pot. And on each branch, the success ones would have 0.8, the failure one would have 0.2. What are we looking for? We're looking for the only branch that has successes all the way along. It should make sense that it would be 0.8 to the power of 10. And the 10 choose 10 is 1 because there is only one branch that that would happen on. Okay? Yes? What is the probability that only 3 seeds will not germinate? How many successes would that be? 7 successes. And what is the probability that more than 8 seeds germinate? So this means either 9 or 10. One way you could do that is use your binom CDF and say if you counted up all of the ones from 0 to 8, subtracted 100 from 1 or 100%, right? You've got a 38% chance that 9 or 10 seeds will germinate. You could also do this in cases. You could figure out, since there's only 2 cases, it's really not that hard. You could find out exactly 9. Well, that's 27%. And we already figured out exactly 10 in part A, so this wouldn't be hard to do it this way either. Add those up and you get the exact same number. The mean of a binomial distribution, or the expected value, has a very easy formula. It's just your number of trials times the probability of success. So if I roll this dice 6 times, okay, my mean, or expected value, how many times would you expect to get a 3? If I rolled it 6 times. This is where your gut should tell you the right answer, probability-wise. How many 3s should I get if I roll it 6 times? 1, right? That would be my expected value. How does that work in the formula? N is the number of trials, 6 trials. What is the probability of getting a 3? 1 in 6. 6 times 1 in 6 would be 1 time, right? If I rolled it 1,000 times, I'm not going to demonstrate. If I rolled it 1,000 times, 1/6 of 1,000, you would expect to get it approximately 167 times. Okay? The variance of a binomial distribution, also on your formula sheet, is quite simple as far as the formula. It's your number of trials times your probability of success times your probability of failure. Which is pretty cool. Which is leading to normal distributions, which is going to be really neat and interesting, but we're getting there. But your variance okay. The variance is on your formula sheet. Standard deviation isn't, but you know that variance is just your standard deviation squared. So if you wanted to find your standard deviation, it's just the square root of this. Are you okay? We should maybe write this above here as well, NPQ. Because 1 minus P is Q, which is the failure, right? They could have used S and F. It would be easier to remember which one's which. S for failure, F for success. But no, P and Q. So an urn contains 7 marbles, of which 2 are blue. Aren't urns what you put ashes in? Yes. So you're playing as a kid. You're like playing the fun game of hide the marbles. Okay. A marble is selected, dusted off, and its color noted. Then it is replaced in the urn. This process is done 50 times. Right? Find the chances that there's less than 20% of grandma left. No, that is not our question. Find the probability that 10 blue marbles were selected. So we see that this is binomial distribution. There's 50 trials with a probability of success 2 out of 7. Binom PDF could tell us that, right? This is one where if you had to draw the tree diagram, it would be enormous with 50 sets of branches. Someone calculated how many branches it would be. 2,500 branches in the end. Woo! And that's, of course, if you wanted to figure it out with your formula, you could do that as well. What is your expected number of blue marbles if you did this 50 times? Well, this is just 50 times 2/7, approximately 14.3. And if we wanted to find the standard deviation, it's just the square root of n times p times q. The standard deviation would be 3.19.